Welcome to the Effect of Pyrometry on Metallurgy presentation. My name is Jason Schulze. I am the Director of Technical Services at Conrad Kacsik Instrument Systems. We're based in Ohio. I'm a metallurgical engineer with just over 20 years experience in aerospace and metallurgy. I'm also a PRI training lead instructor. I teach multiple classes in pyrometry, root cause corrective analysis, and audit preparation. I'm also a voting member of two AMET committees, one of which governs the changes within AMS 2750. Why utilize pyrometry? Pyrometry as a whole exists to ensure that the metallurgical properties are conforming once the thermal process is completed. Understanding pyrometry as it applies to AMS 2750, on the other hand, is not always as straightforward. So understanding how to perform a TUS, SAT, instrument calibration, or just knowing 2750 well does not necessarily mean that one has full comprehension. One must understand the metallurgical effect of pyrometry on the product within the thermal processing. In this presentation, we will go over the metallurgical effects in the areas of thermocouples, instrumentation, system accuracy testing, and temperature uniformity surveys. We will start with thermocouples. Microstructure changes due to heat treating is dependent on, among other things, heat transfer, whether direct or indirect, and its subsequent cooling. Believe it or not, the subject of heat transfer can get quite involved when you start diving into the technical side. This will include plenty of formulas, including the first law of thermodynamics, which will explain the non-stationary temperature fields developed when heating and cooling over time. For now, we will not take a deep dive into this. The point being that heat transfer is an important part of any heat treating process. Some industry specifications require that parts be held at temperature for, say, 30 minutes per half inch of material thickness. This is a consequence of heat transfer. If a material is not held at temperature long enough, the product will not reach the desired temperature throughout and, therefore, will not have homogeneous properties throughout. Product temperature is measured using thermocouples, which is covered extensively in AMS 2750. AMS 2750F identifies 10 different thermocouple types, 6 base metal and 4 noble metal. Those are then split into two categories, expendable and non-expendable. Selection of thermocouple types will depend on what atmosphere and temperatures the sensor will be exposed to. Let's look at some quick examples of this. One of the most common thermocouple types used is type K. Its composition is twofold. One side is chromel, the other side is alumel. Individual colors is yellow and red. Overall extension grade wire is yellow. Usable temperature range is 0 to 2500. As with any thermocouple, type K thermocouples have their advantages and restrictions. Some advantages, they're suitable for oxidizing atmospheres. In higher temperature ranges, they provide more mechanically and thermally rugged unit than platinum, rhodium, platinum, and have a longer life than iron constantan. Some restrictions, they are especially vulnerable to reducing atmospheres, requiring substantial protection when used. Another common type is type R or S. Composition is 10 to 13% rhodium and then pure to 90% platinum. Individual colors black and red. Overall extension grade wire is green. Usable temperature range is 0 to 2700 degrees. The advantages of type R and S is they're usable in oxidizing atmospheres, provides a higher usable range than type K. They're frequently more practical than non-contact pyrometers and has a high conformity to published calibration data. Some restrictions is they're easily contaminated in other than oxidizing atmospheres. Now we'll look at some definitions. An expendable thermocouple is a sensor where any portion of the thermal elements are exposed to the thermal process equipment environment. This is a change from revision E. A non-expendable thermocouple is sensors having no portion of the thermal elements exposed to the thermal processing equipment environment. Typically, exposed thermal elements may create a more sensitive thermocouple, but will also expose the hot junction to the environment, as shown in this picture. The limitations for thermocouple use are based on the fact that thermocouples degrade over time when cycled up and down in temperature. Atmosphere also affects the degradation of thermocouples. If the thermocouple degrades enough, it loses the ability to measure part temperature accurately. With regards to the importance of accurate readings of sensors, vapor pressure should be considered. Vapor pressure of chrome is around 3,000 degrees at atmospheric pressure, or 760 torr. Once a vacuum furnace is around 1 times 10 to the negative torr, the vapor pressure will go all the way down to around 1900 degrees. This means the chrome in type K thermocouples will be depleted in the sensor the longer the thermocouple is held at temperature and that vacuum. It is apparent in expendable type K thermocouples than non-expendable. If a thermocouple is not reading the correct temperature, a process time may be started long before the part temperature actually reaches the desired point. This would potentially cause the properties of the material to be non-homogeneous throughout. It would be difficult to detect this issue with hardness testing alone. A more destructive form of hardness testing would then be needed. We'll now take a look at temperature uniformity surveys' effect on metallurgy. Temperature uniformity surveys, in my opinion, is the portion of AMS 2750 that will have the most dramatic effect on product process in a furnace. Let's begin by talking about what a temperature uniformity survey is. In paragraph 2.2.76, it talks about the temperature variation, which is the temperature variation within the qualified work zone with respect to set point temperature. Temperature uniformity survey test is an assessment of the temperature variation within the qualified work zone of thermal processing equipment prior to and after stabilization. Another important distinction to understand with temperature uniformity surveys is a control zone versus a qualified work zone. A control zone is a portion of the qualified working zone in thermal processing equipment having a separate sensor, instrument, and heating or cooling system to control its temperature. A qualified work zone is the portion of thermal processing equipment volume where temperature variation conforms to the required uniformity tolerance within the qualified operating temperature range as defined by the placement of sensors during the most recent temperature uniformity survey. As you can see, this is an example of a control zone versus a qualified work zone. The control zone is in the circular red. The qualified work zone is the square. The temperature uniformity survey measures the temperature variation within the qualified work zone, which is in the control zone or control zones. It also may be used to establish the hottest and coldest locations if that is pertinent to your process, in other words, type A or C instrumentation. It also establishes any thermal inertia is within acceptable limits. Thermal inertia could also be called overshoot. This will include ramp rates, PID settings, trim settings, etc. To understand the effect of temperature uniformity surveys on metallurgy, we're going to use two examples, one in diffusion brazing and another in aluminum heat treating. We will start with diffusion brazing. Diffusion brazing is used to prevent remelt of the braze joint when the product is exposed to higher temperatures in service. It's typically held just below the liquidus range. There are two braze cycles shown here. On the left is a standard braze cycle. On the right is a diffusion braze cycle. You can see that the temperature is held after the braze at 1950, whereas the standard braze on the left, it is not. In this case, this 1950 hold is what makes it a diffusion braze cycle. Once the high temperature braze cycle is completed, the part should be vacuum cooled to 1950 and held for 40 minutes. It should have a plus or minus 10 tolerance. Hypothetically, let's state that the furnace used could only achieve a plus or minus 25 tolerance. Will the braze joints throughout the furnace be uniform? As you can see, the braze joints do look very different. On the left is a braze joint subjected to the plus or minus 25 uniformity. On the right is a braze joint subjected to the plus or minus 10 degree uniformity. As you can see in the matrix, the eutectic is diffusing into the material, which is the darkish black-gray shading. In between that, you can see the solid solution loops growing on the plus or minus 10 uniformity, where on the plus or minus 25, they're not as prominent, and you can see more of a eutectic matrix still in the joint. Now let's take a look at aluminum heat treating as an example. In general, aluminum is classified as two different types: heat treatable, precipitation hardenable, and non-heat treatable. Following this classification, wrought and cast aluminum alloys are further classified by temper codes to indicate condition. By definition, heat-treatable aluminum alloys are those that can be strengthened by a suitable thermal process for that particular material. Solubility of the alloy elements are directly related to temperature, although alloy element weight percent is also a critical factor. Alloys that contain no magnesium are considered non-heat treatable. The addition of magnesium provides solid solution strengthening without decreasing ductility. Magnesium additions offer strength and corrosion resistance. In general, solution heat treating takes advantage of the precipitation hardening reaction. Its objective is to take into solid solution the maximum practical amount of the soluble hardening elements in the alloy. This process also consists of soaking the alloy at a temperature sufficiently high and for a long enough time to achieve a nearly homogeneous solid solution. To obtain the maximum concentration of magnesium and silicon, the solution temperature must be as close as possible to the eutectic temperature, ideally about 10 to 15 degrees below the eutectic temperature. Control of temperature is critical in aluminum heat treating. If the melting point is exceeded, incipient melting, which is localized melting at the grain boundary, may occur and mechanical properties may suffer. This condition is only detectable by metallographic examination and is irreversible. This is why furnaces used for aluminum solution heat treating are typically required to have a temperature uniformity of plus or minus 10 or better. In conclusion, the question, does it really have any effect on the specific product that I heat treat, will come up from time to time, and hopefully those that perform pyrometry can explain this. While we can explain in general how aspects of pyrometry may affect the microstructure of products, we cannot use that as justification to deviate from requirements. One may not feel that 0.5 degrees above the tolerance during an instrument calibration has any detrimental effect on product. It is nonetheless non-conforming and must be addressed. While considering the metallurgical effect of the different aspects of pyrometry, it is a useful tool to understanding pyrometry from a cause and effect point of view. It is incumbent on the processor to ensure conformance to all aspects of pyrometry. This can only come from continuous training and experience. Thank you for attending this technical session. My contact information is on the slide if you should have any questions in the future. Thank you.